so let's continue. So after this one, we are going to look at actually harmonic oscillator. Okay, so you have probably seen this many times previously, but harmonic oscillator is also very useful concept for describing many other phenomena. Okay, so for that one, let us just start with a kind of basic concept here. Just from classical mechanics, the harmonic oscillator is described as simple spring mass system, right? So in this case, one mass is attached to the spring, and then this is a kind of an initial or equilibrium position, and then we are extending it, and then we let go, and then that is essentially kind of vibrating, and that vibration is simply kind of a harmonic oscillator. And for that one, we are gonna just start with the force kind of balance, that is essentially F equals minus kx, and then k being spring constant, x is the displacement, and then this is like a Newton's second law, right? Mass times acceleration. So here, omega can be defined as a square root k over m. This omega is angular natural frequency or resonant frequency. Probably you guys remember that, right? Like from vibration course. Yeah. So and then from this description you can define potential energy. Okay, just by definition, potential energy is a negative integral from reference point to like this r and then f dr. Okay, and then for this particular case we are integrating from 0, okay, that's the equilibrium position, to extended displacement. Okay, so once you do that, it becomes 1/2 kx squared. Okay, so for this one, if you look at potential energy, that is simply parabola, right? So if I describe this u potential energy versus x, right? So that is essentially parabola case. And then for this one, interatomic potential can be described as harmonic oscillator. Okay, so for this one, let us kind of look more closely. So consider the atoms. Okay, so when we put two atoms with a displacement of x, okay, that is essentially interatomic distance, and then we know that these atoms kind of exert force on each other, right? So for that one, like the way we can describe here is, let me see, oh yeah, this one. If we describe this potential energy, okay, here is x and potential energy, and then if we put far away, right, there is attractive force, and then these atoms are kind of pulled each other, right, pulled into each other, and then as we bring these atoms too close, then there is a repulsive force, right? So that is essentially kind of atoms find the equilibrium position, and for that one, the way we describe here is there is some attractive force range dominating, and then here is a repulsive force. Okay, and then these two forces kind of interact with each other, and then there is a sweet spot here, based on the lowest energy in this case. This spot is essentially called x naught, or in other words, equilibrium position. Okay, this position is exactly where attractive force and repulsive force are balanced, right? That is essentially kind of how these atoms find the equilibrium position. Yeah, yes, go ahead.
Why is it not at the intersection with the x-axis?
So this one is trying to minimize the energy, so the it actually tries to find this minimum point here, because this is attractive force and then repulsive force. Obviously, this one kind of crossing point, but this one is attractive, and then if we go this way, then there is a repulsive force dominating. So it kind of pushed away, and then what's going to happen is that it's going to kind of sit in the lowest spot.
But it can have the same potential energy in just different directions.
If it's the equilibrium, it's going to stay there, right? But but if we kind of put it in like a perspective of like a little bit of excited state, for example, if there is elevated temperature, these atoms will essentially kind of move like a slide, right, around this equilibrium position. So, but like if we look at very stable position, this atom is displaced at exactly S naught. Interatomic distance. Okay. Yeah, that's a good question. Thank you. Yeah. So and then like with this one, like we are gonna apply Taylor series for this this curve. Okay. So we are gonna apply a Taylor expansion for x naught plus delta x. What that means is that assume that there is a slight kind of excitation where we are gonna kind of move around this equilibrium position. Okay, so then for that we can apply Taylor series. So if we apply the Taylor series, there is a ux naught plus delta x. This is just by definition Taylor series. U of x naught plus u prime x naught. This is a first derivative slope of that times delta x, and then this second derivative over 2 factorial delta x squared and higher order terms. Okay. Since we are talking about very small delta x, okay, for higher order terms, delta x cubed, delta x to the power of 4, it gets smaller and smaller, right? So it's kind of reasonable to assume that higher order terms are essentially 0, okay, because we are looking at very small, displacement changes. And then let us look at, this first derivative. If we look at x naught, what is the slope of that? That is essentially 0, right? Do you see? Because that is the lowest point. And then if we look at the slope at this equilibrium position, slope is 0, right? So that is why this second term goes away, because slope itself is 0. And then the first term, u of x naught, this is just reference point, okay? Because potential energy is always, reference to something, right? So, they can be just kind of chosen as 0, okay? So it doesn't really matter, okay? So this is essentially reference point. So, we can set it as a 0. So what that means is that the leftover term is only this term, right? And then that is 2 factorial is 2, 1 over 2, u 2 prime x naught, right? Second derivative, and then delta x squared. And then this second derivative is just, like it can be just simply constant. So what that means is that, this description is exactly like harmonic oscillator, right? 1/2 constant x squared, right? And then if we look at the harmonic oscillator, what was the potential energy? That was 1/2 kx squared, right? So in that sense, this interatomic potential, just if we simplify that, it's essentially like what? Harmonic oscillator, right? It's just like harmonic oscillator. So, I mean, this one can be also kind of understood as, this is essentially kind of mass, and then there is some interatomic force. That force can be represented by the spring, right? In the sense, mass spring system. Okay? So that is simply harmonic oscillator. And then with that, like we are gonna solve for Schrödinger equation, okay? Because we already know what the potential is for this particular case, right? And then you can apply this potential energy into the Schrödinger equation. So in this case, you are essentially solving Schrödinger equation for interatomic potential, or generally harmonic oscillator. Okay. So in this case, we are going to apply the boundary conditions. So boundary condition in this case is, like wave function at x being negative infinity or x being positive infinity should be 0. Okay. Because think about it, like x, like we are essentially displacing it, but x goes to infinity or x goes to negative infinity, probability density function has to be 0, right? Because this x cannot be extended to infinity. Okay, so that's why like we are setting these boundary conditions. Okay, this psi x being negative infinity or x going to negative infinity, positive infinity must be 0. Okay, because probability density function, right? Probability of finding this, this mass as x goes to infinity or negative infinity must be 0. Okay. And then this one is actually kind of very lengthy process to work on this Schrödinger equation. So I'm not gonna get into that, but I'm gonna just kind of show you the results. Okay, so after going through, you know, like a very lengthy process, you know, like energy is essentially given as this one. Okay, so if you look at it again, this one is a discrete energy. Okay, because energy is given as n plus 1/2 h bar omega. Okay, and this n goes from 0 to infinity, but with only integers. Okay, so it's kind of again discrete energies. So the lowest energy is 1/2 h bar omega, right? And it's 0. But the next available energy is 3/2 h bar omega, and then the next one is 5/2, 7/2, and so. Okay, so there is a definitely energy gap. So meaning that, you know, this is a discrete energy, and then wave function, you know, by solving this Schrödinger equation is given as that. Okay, I mean it's quite complex, right? If you look at it, this is a square root m omega over pi h bar, and then 1/2 to the power of n factorial, and then the whole thing to the power of 1/2, and then there is hn. Okay, this is called Hermite polynomial. Okay, so, you know, for example, if you just plug it in into Hermite polynomial, there is actually kind of given equation. If you plug it in, there's another equation that spit out, you know, the value, and then, you know, there is an exponential term. Okay, so again, this omega, okay, this omega is simply natural frequency or angular or resonant frequency. That's square root k over m. This nu is related to 1/2 pi square root k over m, because, you know, this omega is simply 2 pi nu or 2 pi f, right? So, you know, as I mentioned, I'm gonna interchange this nu and f, you know, freely in this course. Okay. So we got this wave function. Okay. So, and then, you know, let us kind of look into the difference between classical approach and quantum approach. Okay, because, you know, like this is essentially quantum solution, but we know a lot about classical, you know, like a harmonic oscillator, right? So let us look into that. So classically, you know, this is essentially kind of how it's described, right? Was initially this mass was located at x naught, but now we are extending it further, right? And then we kind of let go, and then it will kind of oscillate, right? So if we actually kind of describe this one in terms of energy, it can be drawn as this, okay? Or maybe I'll just kind of match this one. So here, this is kind of the initial point, and then the parabola is going to look something like this. Okay? Or maybe I'll just kind of exaggerate too much. Okay, so like this way. 0 point and here. Okay? So in this case, you know, throughout this process, right, this is essentially, I should position or x, and then this y-axis is the energy. Okay, the total energy is conserved. Yes, for example, this total energy is essentially kinetic energy plus potential energy. Okay. By the way, this one maybe if I just represent this as essentially blue, this one is essentially potential energy, right? This potential energy was a 1/2 kx squared, right? So in the sense, what graphically what this one shows you is that this much is the potential energy, but the total energy needs to be conserved. Okay, right? Total energy is essentially kinetic energy plus potential energy. So what that means is that, you know, the difference here. Okay. This one must be what? Kinetic energy. Right? Does it make sense? You know, like for example, if we basically, you know, the mass is moving basically between here and here, right? It kind of goes back and forth. And then let us look at this end point. Okay, let us look at this end point. what is the velocity at the endpoints? Zero, meaning kinetic energy, zero, right? Potential energy, maximum, right? And then as we kind of move back, and then if we kind of pass through the origin, kinetic energy is maximum, right? Because that is essentially kind of where you expect the largest velocity, right? Does it make sense? And then, potential energy being zero. Okay, so that is essentially kind of how you can see. And then if you look at this classical approach, this energy, okay, this energy is continuous. Do you see that? It can locate any points, right? So for example, energy is continuous. It can be any points, okay, if you look at this plot, right? So energy is continuous, okay? This U is continuously changing, or this energy, the total thing, is essentially kind of fixed, okay? So in the sense, like another thing I want to mention here is, let us look into this area. The mass, this is essentially, like, can we find mass in this highlight regime? This is essentially kind of position X, right? In this highlight regime, classically impossible, right, to find the mass. Does it make sense? Because like if we describe here, it's going to be located here and then come back and come here, come back, right? And then if we look at this particular potential energy, it'll go up to here and then it'll go back like that, right? But it cannot reach this point, for example. Does it make sense? Are you guys following? Classically, like what that means is that this mass is really confined within the plot, right? This highlight regime, the mass can never reach, right? So that is a kind of the classical approach here. And let us look into quantum mechanics here. Okay, we are essentially looking at this solution. Okay, this solution. Okay, this part. So for that one, let me just kind of bring this plot here. Okay, let us look into this one. So if you look at this one, there are like several plot. This is essentially wave functions. Okay, so this is the wave function corresponding to the lowest energy, and then this is a wave function for n is 1, and then this is like wave function for n is 2. So in the sense, the lowest energy, the next available, and the next available energy, and so on. Okay, so again, what that means is that like the energy is discrete now. Okay, because it's no longer continuous. The energy has to be this much, or 1/2 h bar omega, and then the next one, and then so on. Okay, and another part you can kind of look at is this wave function. Like if we consider probability density function, we have to now obtain the complex conjugate wave function and multiply by wave function, right? So in the sense, it's kind of basically square. Okay, when we consider square, do we have non-zero values outside of the this parabola? We do, right? So if you look at it, the value here is non-zero, right? Value is non-zero, value is non-zero. What does it mean? In quantum mechanical approach, in this highlight regime, you may be able to find this mass outside of this parabola. Does that make sense? It's kind of again like tunneling idea, right? Classically, you cannot really go above or beyond this parabola shape, but quantum mechanically, there is non-zero value, meaning that there is a still chance that you can find this mass outside of this parabola shape. Does it make sense? So meaning that if we classically, let's say, if we operate spring, okay, and then for given potential energy, right, given like how much we extend, let's say classically it confines the movement like that, okay, then classically it can never go beyond that, right, this much. But quantum mechanically, what this one's saying is that, sometimes you may be able to find this mass locating here, right? Again, kind of tunneling idea. Okay? So, classically impossible, but quantum mechanically possible. Okay, and in this case, again, like the ground state energy. Okay, the lowest energy is 1/2 h bar omega. Okay, so in this case, like the classically it can reach 0, right? The potential energy, but here in this case, ground state energy is has to be some value here, 1/2 h bar omega. Okay? So and also discrete energy. Okay, energy is no longer continuous. Okay, the particles can only sit in like a certain values. Okay, and then discrete energies. Okay, so with that, let me just kind of go to another kind of the description here. So for this one, let me just bring another plot here. So this one is the case for probability density function, right? The probability density function. For when n is 12. Okay, so it's a little bit higher energy. Okay, it's not the ground state energy. So in this case, again we are looking at harmonic oscillator. Okay, so how does probability look? Like classically, if we consider, classically, let us think about how the probability would look. Okay, maybe might be confusing, but so when we kind of look at this classical kind of harmonic oscillator, as this one keeps moving, right, left and right and left right with a different speed, right? So basically meaning that as it reaches to the end point, the velocity is 0, but velocity is highest at the center point, right? And then, in terms of kind of when you observe, what is the probability of this finding particle m or mass m, at a particular locations? That is essentially kind of what I was kind of asking. Okay? So this one, it keeps kind of moving from left to the right with different speeds. So what is the kind of most likely position, in terms of finding this particle m? So when the velocity is 0, right? So basically, as it kind of moves, as particle moves left to the right. So for example, when it kind of this one accelerate fast and then goes slow, and then 0 point, and it comes back, and then it accelerates, and then it kind of deaccelerates here, and then slowing down, and then 0, right? Does it make sense? So in the sense, you naturally expect endpoints, basically the particle reside at the longest period. Does it make sense? Right? So in terms of that. So what that means is that, classically you would expect probability kind of like parabola. And then quantum mechanically, this is a probability density function. So look at the kind of this shape. Which area has the highest probability overall? Endpoints, right? Endpoints have a kind of highest probability. So it's kind of similar to classical approach, right? It's kind of similar to classical mechanics here. So in the sense, basically looks like parabola. Okay, so basically meaning that higher chance at endpoints or turning points. Okay, so this one is essentially kind of similar to classical case, right? But the difference here is that, you know, this probability kind of oscillates, right? So for this particular case, the probability of finding this mass at this particular location is essentially 0, right? It's kind of, you know, this kind of oscillates. Okay? So for classical or for quantum mechanics, you know, like the probability of finding this position, probability of finding this mass at this particular position, right, is essentially 0. But classically, you know, I mean, that's not the case. Yeah. All right. Okay. So with that, let me just kind of go